You all have USB devices. You're about to become very scared of them, I think. Really happy to have Kate and Mikaela. They work with Great Scott Gadgets. They're going to tell us a whole bunch of stuff about USB. Looking forward to it. Thanks. Take it away. I think this is on.
All right, good to be able to have a microphone. This is amazing. So, welcome, Kate Temkin. This is Mikaela Szekely. Give you bio slides in a second because I know everyone loves those. But this talk is on making USB accessible. I am almost definitely doing this talk going to walk away from this microphone. So it is wireless, but that'll probably work better. But if I start pacing too much and it starts being super distracting, just yell at me. Same thing if I talk too fast. So this is, the proper title is Making USB Accessible. I like to make slide titles that I cannot fit on the title slide, so this is the short version, but you are in the right place. We are going to be talking about USB tools, and though there are some scary stuff about USB, especially in USB 3 and 4, the USB 4 being forthcoming and looking a lot like PCI is kind of scary to me. The kind of goal of this talk is to demonstrate that USB is, with the right tooling, a pretty accessible thing. So really, the lack of tools are the thing that's kind of creating that gap between accessible USB things and accessible USB access and where we are right now. And hopefully we'll be showing you how we've started filling the gap. So I'm Kate Temkin. I lead the software division of Great Scott Gadgets. My business card says hardware hacker, which is probably a better description, considering though I am the software lead, as you'll see, build hardware as much as I do software. I mostly focus on educational reverse engineering stuff, so I love education and I have a less favorable opinion of a lot of the stuff related to information security. So I much prefer building things to breaking things, though I've done a fair amount of both.
And then I'm Mikaela Szekely, handle Kyriad, and I'm a student, which means obviously I know everything. And especially after meeting this one, I managed to dive into open source USB stuff and got really deep into it.
Yeah, and there's no coming out now.
No, definitely not.
So one thing that is a kind of a fundamental difference between us is I am apparently a cyber criminal, according to the Daily Mail. Mikaela is not. We both worked on the same thing. She actually manages and maintains some tools for an exploit I wrote for the Nintendo Switch. But apparently, I'm the cyber criminal.
I wasn't caught.
Yeah, apparently Mikaela is better at cybercrime. So here I am, cyber criminal. I love this slide. Especially as, and I keep using this slide over and over again because this is like the best press I've ever received. By short-circuiting a wire, apparently I can reach the most basic command level of the Nintendo Switch. And then I can run whatever software I wish. So if you have licensed software, sorry, it's mine now. So I'm going to start this with a story. And hopefully the story will go and kind of continue into USB and I won't ramble distractedly. But so this started with a USB training. I actually maintain a few open source USB tools, including FaceDancer, which was it's a library for emulating USB devices. And there was originally a training that's kind of, I think the name with FaceDancer is growing more and more stale. But this was a training where we taught students the basics of USB. And I've offered this with Mikaela, I've offered this kind of before that point. And this is a really neat course where we kind of cover USB from the ground up and get to the point where you're hacking on USB devices, both figuring out how to reverse engineer them, figure out how to use them for things other than their intended purposes, kind of the true hardware hacker model of how do I get into this and how do I make it do something that's cool and neat and not its original purpose. And so one of the things that was necessary for this tool, one of the things I wanted students to be able to do when they started off the classes, I wanted them to be able to pick up their USB boards, their target boards, and get a set of packets out of this thing just kind of off the bat. So I wanted them to be able to do USB analysis. That normally would require a piece of hardware, which we really don't have the budget for in a training kind of environment. Students are paying for their own tickets. If I include USB analyzers in those tickets, or use of USB analyzers, the ticket price is going to go way up. So what we have been doing is using USBmon, which is a Linux kernel module that gives you an insight into the Linux USB stack. USBmon is kind of, it's a nice thing in that you get to see Linux's view of USB, but you get it in a very Linux-centric format.
Pretty much, you get it in the format that Linux likes to request data from. That Linux's view of how USB works, and that is very. It's not super. It's not super
straightforward.
It's not straightforward. It's because the kernel has its own model of how to interface with USB. That doesn't mean that that is a model of USB itself.
In the USB group here. I have a new group myself. This is the fun thing about live demos.
Also, keep in mind you're not presenting as well.
Yeah, I'm new grouping myself here. Have multiple monitors going on, but Wireshark. All right, so if we run Wireshark, what we see is a interface that looks like, I think OpenOffice is going to need me to close the slides for a second. I've started using LibreOffice, which is kind of its own terrifying challenge. And so if you look at Wireshark, what you get here is a collection of devices that are kind of intended to be, to give you USB analysis, they're going to give you IP analysis, not USB analysis. And so if you open Wireshark and you tell it to look at USB packets, what you actually see is a bunch of kernel data structures. You'll see collapsed immediately something that says herb, and that's it. Herb is a USB request block. It's the Linux kernel's view of USB. You'll start seeing things like status equals negative E in progress, or status equals negative E no dev, or status equals negative pipe. Those have absolutely no mapping to USB. So USBmon is a great thing because it's free, but the tools that parse USBmon data kind of suck. And so given the cost requirements, I've handed this to students numerous times, and I think it's pretty fair to say that they've been kind of baffled by the way Wireshark outputs this data, baffled by using the tool. It's not super straightforward. If you scroll down there's a USBmon device. There's several USBmon devices that correspond to the USB buses on your computer, and one that coalesces all of them. And just there's absolutely nothing that tells you what any of this stuff means in a USB level. You can see some of the data that's carried by USB, but there's not a one-to-one mapping between Wireshark and USB packets. So that's definitely a challenge in using this stuff.
USBmon as is gives you again a kernel-centric view of USB, and then you feed that through Wireshark, which was made for like TCP analysis. So you're kind of fitting the kernel's view of USB into a sort of TCP model, and you end up with weird things like that.
So we have a tool that gives us USB analysis, but it just doesn't go far enough. It doesn't actually give us a view of what's going on in USB terms. And it is filtered to the kernel, so if something goes wrong, the device doesn't show itself to Linux. If Linux doesn't actually get packets out to that, there's nothing that's going to say, hey, this really early problem happened here. Some of those packets that are done in the early enumeration stages, in the early device discovery stages, are consumed by Linux, and it doesn't forward them to you. So if we want a much truer to reality view, we can start using devices like this super cheap SIGROC-based logic analyzers. And so these are generally inexpensive if you order them from across the world. And things like AliExpress, you can find these things for $3 or $4. If you want them off Amazon, they're $7.90. They're like $7 Prime, $6.99 Prime. I love the 1-star review on these things. It's by these are very cheap devices, and I think people have both the wrong expectations of them and a misunderstanding of what logic analyzers are on Amazon.
Not just a single, like, it's not just 1 star. Isn't that like a single? Yeah,
There's
that's
a
a single
one
one-star
star
review.
So these things are really freaking cheap, and they can capture up to 24 megahertz, which is enough to analyze low speed and full speed USB. This does not exist for high speed USB. So if I want to use this with my training course, I have to arbitrarily limit my high speed device to full speed in order to kind of see those packets, and I don't think that's a great experience for students either. So SIGROC will do low speed, full speed analysis up to the point where it's breaking things down into requests, but it doesn't really tell you what this request means. In this case, this is 08, 06, and if you actually look at that setup, the packet, the data stage of this setup packet, you can go, and if you're really familiar with USB, you can recognize this as, oh, it's asking for the device descriptor. SIGROC doesn't tell you that. So SIGROC is great. libSIGROC decode is great. It's awesome at getting USB packets out of your traces and captures, but it doesn't go far enough.
And you can't expect people to just look at some hex from a USB packet and know what it is unless you're a USB wizard.
Yeah, like me at dinner the other night at Autodesk, I was sitting there like someone was reading me USB text. I was going, yeah.
Yeah, you just decoded the matrix of USB on the fly.
It is kind of like this matrix where the guy is saying, like, I don't even see the numbers anymore. But yeah, so the state of the art in these things, if you want something that gives you good high-speed analysis, if you want something that's going to give you a breakdown of packets into their component pieces and kind of give you the full protocol, you are talking about something that is $1,100 in singles. This is the cheapest one that has that kind of software capability right now that is usable, really. There is a low-speed and full-speed version that is only $300, which compared to the $3 board is kind of a hard price tag to swallow. But this thing is really nice to use in a lot of ways if you're doing USB stuff. It's just also really inaccessible. Yeah, you're paying for the software on this thing. I'm a bit of the hardware, but there's a lot of kind of leading to this conclusion where people kind of say, isn't USB this really complicated protocol? Don't I not want to take my microcontroller and implement USB? And USB really isn't that complicated, especially for things that are just, hey, I want to get a little bit of data over the bus. But if you can't see it, it might as well be magic, right? So if you're just setting your microcontroller up, something's not going right, Windows is saying, hey, this isn't a valid USB device, or Linux is spamming device won't accept address 0, or device won't accept address 1 repeatedly in dmessage, you're gonna think that USB is kind of black magic. So the fact that tools aren't accessible makes people think that USB is this kind of mystical, crazy black magic. For low speed and full speed, it is absolutely not black magic. Once you get up to the kind of super speed level, it gets a little bit more complicated, and theoretically, USB 4 is going to be sending PCIe frames over it, so...
Yeah, USB 4 might be black magic.
That's a hell of an abstraction stack.
We'll stick to USB 2 mostly for now.
They haven't released the spec in its final form, and they've only really talked about what's in it, so
yeah.
Our conjecture about USB 4 is that it may be black magic. So USB is inaccessible to the point where people don't really want to test their USB devices. This is an output of some data captured from the NVIDIA bootloader that's present in every NVIDIA Tegra device, every one of their embedded devices, up until the Tegra X1, which is the processor both in a bunch of the Tesla control centers and the little kind of infotainment system that both controls some of the car functions and displays a bunch of things, and in the Nintendo Switch.
And the Shield TV.
And the Shield TV, and a bunch of things like that. This is the most famous example here I think that people are aware of is the Nintendo Switch. Mm-hmm. And it's kind of, I've joked around that if you want something red teamed, hiring a red team is not as good an option as just putting it in a game console. But this device has a pretty severe USB vulnerability that allows you to completely compromise its root of trust. It's a really simple vulnerability, especially as if you look at the get status request here, this request that has the vulnerability is request number 0. So if you're iterating through all of the different requests and trying to see what is actually vulnerable on these devices, well, you start at 0 and you end at 0. So this is actually just a packet that's saying, hey, normally it'd say, give me 2 bytes of status. And I said, give me a whole bunch of bytes of status. Give me something like 65,000 bytes of status. And what I get back is an obligingly large amount of status data.
65,000 bytes of status.
That data itself happens to be copied into a tiny DMA buffer that is only 4096 bytes large. So copying 65,000 bytes into a 4096 byte buffer, not super fun. Not for the device anyway. I was not the first person to want an open source USB analyzer. Not by far. There was actually a fairly major Kickstarter that was funded back in 2010 by Bushing, who is a failoverflow fame, and Bushing created a device called OpenVizsla. OpenVizsla, I think, is well known as being one of the longest Kickstarters longest Kickstarter production time to actually deliver, because I think they didn't get the boards out until 2014, after a long point at which people kind of assumed this project wasn't happening. The OpenVizsla board is relatively simple hardware. If you have one of these like I do, sitting on this table here, then you can do some really basic USB analysis on a device that it was $250 when the Kickstarter started. Now it's about 120 euros, which is just under 150 bucks USD, plus shipping. For a while, you could not buy these anymore, but stock has been found. They are available again. They are pretty good USB analyzers if you're willing to deal with the software. One take as I set this up.
Yeah. So the OpenVizsla in particular is also, as well as the Total Phase Beagle, is also high speed, which again, like, is at just under $150, is considerably more accessible than 1,000 per piece. But again, the software for OpenVizsla was a bit lacking.
Here, I'm gonna kill him. Once I figure out what my mouse is,
Your mouse is on the terminal. You gotta kill Wireshark.
start this. You wanna narrate what I'm doing? I'm putting the microphone down.
So what we have is a tool that Kate kind of rewrote most of OpenVizsla's software stack.
Yeah, we'll get to that. This is actually the original OpenVista.
Oh, is it? Okay. This is what you get. Well, this is the startup.
Right. So right now, OpenVista is saying there's no USB device plugged in. I'm going to plug in a USB device. I had another one on my desk, but at the last minute, I decided to plug in a Great Fat because I figured I should use my own products and demonstrations.
It would help to analyze a USB device instead of just air.
All right. So this is interpreting USB packets. This is not incredibly useful. I'm going to restart the software, and hopefully we can see kind of this thing not repeatedly requesting data. Any here now, my terminal will stop outputting the data for the thing I canceled. If it actually wants to. That is not the right output tab. Did that die yet?
Oh my God, no.
Nope. Okay, just kill it. That way. So, ooh, that's fun. So OpenVizsla gives you a really, really, really difficult to interpret USB packet level view.
It actually kind of ends up giving you a very similar view to what you get with SIGROC's Pulse View. You get the packet ID and you get some hex.
So
again, it can do high speed, so we've improved from using a logic analyzer.
And I don't know if you'd call the user experience right now super desirable. This is the out-of-the-box experience with OpenVizsla. And so OpenVizsla has a really, really, really well-defined hardware layout, hardware design. It has boards that are very well tested, but what it lacks is an actual kind of environment for doing USB analysis in any meaningful way. So if I take a Great Fat device here, And let me just plug it into my computer, and we'll see the kind of enumeration of this device from OpenVizsla's perspective. All right, so what we see here is actually the device enumerating itself. And if you are really familiar with USB, you can take a look at all of this output and say, okay, I have basically the same thing we saw from SIGROC, but for a high-speed device. This is the host actually requesting the device descriptor. This whole piece here is a control transfer. It's one simple verb asking the USB device to describe itself. But unless you happen to speak raw USB in hex, and you can go say, okay, well, 8.0 is actually an endpoint 0 standard device request. It's asking the device for information, and the next byte is 6, so it's a get descriptor request, and the next byte is 1, so it is a get device descriptor request. Unless you know all that stuff at the top of your head, this is not super useful to you. You need something to parse and process this.
And OpenVizsla also, the software will not group anything. A lot of USB packets are logically grouped together, and then those are logically grouped together, and the OpenVizsla software will just show you them by themselves.
So OpenVizsla exists. It's still kind of on the expensive side of what I want. I would love something I could hand out in trainings. So there's kind of a commonality between the things that exist. They're expensive, especially if you're kind of looking for something you can hand out in trainings, and the software stacks that drive them are very, very, very difficult to interpret, to use, to work with. So USB, kind of one of the driving problems there is that USB is very, very, very fast at high speed. The data signaling happens at 480 megabits per second, which means that toggling on USB happens at up to 480 megabits per second, and the voltage is relatively low. So that's how they get the signaling as high a speed as they do, is by pulling the overall voltage swing very, very low. We have a lot of difficulty sampling that on even high-end logic analyzers. If you take a Szekely's 500 megahertz analyzer cannot sample USB high speed, because even though theoretically 480 megahertz is less than 500 megahertz, the sampling is not synchronous to the device. It's not synchronized to the device's clock, which means you need to sample a bunch of times in order to figure out where the clock edge is and see that USB data.
Ideally twice as fast.
More than twice as fast. Ideally, like 5 or 10 times as fast oversampling. Nyquist says theoretically you can do it at twice as fast and see the frequency signal there, see the toggling, but it's really difficult to do clock recovery on things that are that slow. So if you are a digital device and you want to capture USB high-speed data, you need to be at like 5 to 10 times the speed of 480 megabits per second in order to be able to figure out when the USB signal is toggling, in order to be able to figure out when you should sample that USB signal.
And high-end logic analyzers, even high-end logic analyzers, that's going to be a bit difficult to...
Yeah, you have a hard time finding logic analyzers above like 500 megahertz in common use. Even multi-gigahertz scopes have difficulty with this. So what we have here is a device called the USB PHY. It's the physical layer for USB. This device is the key to cheap USB analysis, because what it does is take all of that nice USB data that coming in at 480 megabits per second, sample it, do clock recovery, and spit it out as 8 bits of parallel data at 60 megahertz. Right, 480 divided by 8 makes sense to get 60 out of there. And what that means is that you've taken something that was well outside the range of what's sampleable by a cheap device, and you've pulled it into that kind of range. And this is actually one of the operating things behind the OpenVizsla design, is they take a USB PHY, use it to decode or to deserialize the USB data signals, and then squirt them into an FPGA, which does all the processing. So essentially, the PHY is our kind of magic bullet for this, because it handles all of that clock recovery, it handles all the deserialization, and it puts everything in a domain that we can be synchronous to. So we can easily sample this on a lot of different pieces of consumer hardware. One of my favorite things to use on this, one of my favorite microcontrollers, is the LP34330. The LP34330 is amazing in that it has a synchronous, really configurable serial engine called SGPIO, or serial GPIO, that you can use to construct all kinds of different serial peripherals. So this thing is capable of sampling 16 pins at up to 204 megahertz, putting that in device memory without requiring any CPU time. The LPC4330 has on board either 2 or 3 microcontroller cores as a Cortex M4 and 1 or 2 M0s. This thing can do all of that data capture without using any of those cores, which means that any post-processing you want, you can do with this device. Also has a really, really, really neat feature where it can do all of this sampling, not just based off an arbitrary clock, but you can add conditions to it. You can add shift qualifiers, so you can have it only shift in data when the data is indicated as valid by another device, like your PHY. You can also do pattern matching on the data that you shift in, so it doesn't bother storing things unless they meet a certain mask pattern. So this is a really, really, really powerful serial engine, and it's really fun to write the drivers for this thing, but like several weeks to get a fully general driver working.
But being able to pattern match against this lets you, like, we already have enough speed for high speed, but even aside from that, you can pattern match against things that we don't care about, like USB start of frame packets or start of frame fields.
Right, so given that you're capturing data to a microcontroller now, you need to be very, very, very frugal about what you are capturing and omit any unnecessary data. Even if you add a big SD-RAM chip to that microcontroller, you need to actually make sure that you are not capturing excess data, because at some point you're going to need to take all of that data that's on the SD-RAM and forward it up to the host, right? And that means that you are going to need to saturate a USB bus, and if you're going for inexpensive, you're still talking high speed and not super speed, which means any more data than is necessary is going to be a real headache for you. Full disclosure, the company that I work for, the company that pays me, manufactures this board. This is one LPC4330 board. I feel okay talking about it because it is open hardware, so it's fully open source, which means you can build them yourselves. You can go and buy these boards pre-made from various people, but if you have a few hours and a soldering iron and you're comfortable soldering TQFPs and 0603 surface mount parts, you can put one of these together using just the parts you buy off DigiKey and the board you buy off Oshpark. So by all means, build these yourself. They have, this board kind of acts like a prototyping crucible for doing things like capturing data from a ULPI PHY. It has a USB stack that has been written by a bunch of people. I've since done a little bit of rewriting on it to reduce the amount of CPU that it uses, but it has a super fast USB stack, which can basically saturate USB buses, which is rare to see on a microcontroller. So this is a high-speed USB port here that is capable of actually, on the regular, outputting 40 megabits per second, 40 megabytes per second to a USB high-speed host. And it can saturate the bus, so depending on your individual host, you can start pushing up to like 50 megabytes per second. I keep saying megabit. So this is a very, very, very fast USB peripheral. And this thing has some very generic SGPIO drivers that are super easy to configure that let you just take sets of parallel data, write some little structures to say, okay, I want to use these pins, these are the conditions under which I want to shift, and that data will just be streamed right up to your host without you doing really much at all. Provide a little structure that describes it, and you say start USB streaming, and the device does it. So this is kind of a cool multi-tool for hardware hacking. I like to think of the LPC4330 is an amazing microcontroller for this stuff, both because of that streaming serial engine and because it has 2 USB ports on it, one high speed and one full speed. If you buy the version that comes in a BGA package instead of the version that comes in TQFP, it has 2 high-speed USB interfaces. One of them has a physical PHY built into the chip. The other has a ULPI output, so you can hook it up to something like this PHY, and it'll handle all the USB stuff for you. So I love this thing for doing fast USB style hacking. It is a face dancer board, which means that you can emulate other USB devices with it. It has support for something called USB proxy, which is another tool that I maintain. So this is kind of an awesome board for this kind of stuff. And really, that's because this chip is an awesome chip. That kind of brings me to what's called GreatFET rhododendron. Every one of the GreatFET devices is codenamed after a flower going in alphabetical order. We have since run out of alphabetical letters, so I think we're looping back around to A. But GreatFET 1 was codenamed Azalea. This board here is codenamed rhododendron. And rhododendron is essentially just a USB PHY, 2 USB ports connected to pass-through USB, some support hardware, sitting on top of a GreatFET neighbor, neighbors being the boards that plug into this header. This is a prototype that's designed to answer the question of how much USB can we capture using just a ULPI PHY and no SDRAM. So the GreatFET itself has only about 300K of flash, but it can get data out very, very, very quickly. And so the question kind of becomes, well, what kind of USB traffic can you capture just using that? Is it enough to hand this 10-cent to dollar PHY, depending on your quantity, on a board to students and have them be able to analyze most high-speed devices? And the answer, amazingly, is that this can actually do more high-speed stuff than you'd expect. This is good for anything that doesn't have sustained little bursts of packet activity. So if you're just doing enumeration stuff, that's pretty easy. That's just saying, okay, who are you? What do you do? That's sending little tiny exchanges of data. That we can do super easily. Surprisingly, things like flash drives that are bulk devices that you think of as fast devices when you think of USB, we can capture those too, because usually those high-speed flash drives are limited by the controller on the flash memory. They tend to peak at about 30 megabytes per second, which is well within what we can actually get off kind of live streaming from the device. So it turns out you can do a lot of USB capture using just a ULPI PHY and no RAM buffering.
Especially since it's considerably unlikely that you'll have to analyze a device that will consistently saturate the bus. It's honestly more likely that your host, your computer, will not have a host controller that's fast enough to sample this, rather than the GreatFET being the limiting factor.
Yeah, but then again, you have kind of the difficulty where it's interesting to see how the interplay of various devices works with that, because if you plug rhododendron in with another device on the same host, if you're analyzing that device, who knows how that's affecting things, because it slows down both the rhododendron's ability to capture things and the device itself. They're competing for bandwidth now. It doesn't really change things that much. If you plug in another device that's not the device you want to analyze, often that will actually wind up interspersing its packets with the first device. So analyzing 2 flash drives and analyzing one of 2 flash drives that are plugged in can be easier than analyzing one, because they have to share the bus, and suddenly you have half the bandwidth to report up to the host.
Is there a technique that you could use? Even if you do come across a device that saturates the bus, just plug in a flash drive and start a file transfer?
If you have that kind of thing, theoretically, yes. So the recipe for a high-speed analyzer here is really just a microcontroller that has the ability to send data to a host fast. Theoretically, a lot of, I think Cypress chips have a similar thing. The FX2's FIFO isn't good enough for this, but the FX3, which is a super speed chip, has something that's very akin to SGPIO and a really fast pipe to your host that also tend to be expensive chips. FGDI has a FIFO chip that is almost good enough. It can't do enough to capture ULPI data by itself. So you need something to help it translate it, like a tiny ICE40 FPGA or something like that. But you could do an ICE40 FPGA and a FIFO chip. And there are plenty of boards that do that already. I'm looking directly at Piotr. This Icebreaker board does a similar thing. But you put some kind of digital processing on here. I like the LPC 4330 because it's all in one, it's an all-in-one solution for that. You want to put probably an SDRAM for packet buffering. This is pretty optional if you want to produce an ultra-cheap device, because essentially that SDRAM is the thing that is driving up your cost. Because you pop an SDRAM on there, they're both kind of expensive parts for significant size, and your board becomes complex enough that you're switching to probably a 4-layer design where you could have been doing a 2-layer. So having to do all those nice trace match patterns for the SDRAM controller means that you're going to have a lot of difficulty crossing your signals across the board. So having that SDRAM does significantly buffer the price and makes this difficult to make as cheaply. ULPI PHYs are less than $1. even in single. So they're super cheap. You can buy microchip parts, the USB 34XX series. It's hard not to say 4330. Those PHYs are like 30 cents in reasonable quantities, like hundreds, and much cheaper if you buy them in thousands. And for the LPC 4330, the variants that do not have flash on them are actually cheaper than the variants that do. So a little SPI flash ROM and a LPC 4330, for example, is cheaper than one of the LPC parts that has onboard flash. And so this gets you a really, really, really super cheap overall design. The LPC 4330 is about FTDI price. So you're talking around $5 in reasonable small quantities for a 2232H, which is the fast one. So this is like a FTDI that's much more capable if you're willing to write a little bit of software or use ours. This is about $5. SDRAM really varies a lot. If we omit that, we have a $5 part, a less than $1 part, a less than $1 part. Put together a PCB, PCBA, that's really going to depend on how you produce things, but you're still talking about a device that has a BOM cost that is super low. Right? This thing's less than $10 in BOM cost at any reasonable quantity. So you get a super cheap analyzer that's capable of doing a ton of USB stuff. If you compare this to $1,100, this design looks pretty good. So hopefully we'll get to the point where I can start taking the rhododendron design and giving it to people who are already getting great feds in a training. And eventually my goal is to take this and once that's kind of has a stable design, move to something that is a dedicated board that has kind of the USB hacking tools all on one board, like an LPC 4330 has both of those USB ports brought to headers and then has the ULPI PHY connected such that you can do this kind of analysis. So this is a super, super cheap design. And I love the fact that this is really all that you need to do most analysis in hardware.
Though we just figured out, okay, good, we can build a hardware analyzer. But we also realized kind of embarrassingly recently that we still have the same problem with a lot of the things that we talked about before. We need software to actually do something with the data that we get from our hardware analyzer.
So if you're the kind of person who thinks of yourself as mostly a hardware engineer, you are probably in the same boat that we were, where you have a prototype and a proof of concept in the form of some really simple microcontroller code, and you kind of get to the point where you're like, wait a minute, this thing actually needs some software. I got back from hardware.io where I gave a workshop last week on Sunday. I got back late at night, Monday morning at 6 a.m. Initial commit on the USB analyzer software.
So when I say embarrassingly recently, I mean less than a week ago.
So when I show you this stuff, I think the stuff that we've produced looks really good, and that is especially within the context of this being 1 week into the design for the software. I am super excited about the software to the point where I woke up this morning and started trying to add more decoders and features to it. Even though I was giving a talk on it, I was kind of afraid to touch the code base.
Not just that, to the point where you were trying to modify it less than an hour before this talk.
I was not this thing has a really good working demoable state that it's in, so it's not just trying to get it done at the last minute. This is just I super love the way this thing is.
Oh yeah, this wasn't you need to fix something. This was just you don't know when to stop.
Yeah, that's definitely a problem I have. So initial commit Monday, Tuesday, implement most of the analyzer. So I'll talk about the software, because I think the software that we're building here kind of winds up being a distinguishing piece of everything. Do you want to kind of walk through the architecture?
Yeah, so the architecture is... The architecture itself is very modular, and to the point where the backend and the decoders and the front end all run in separate processes. The backend is what talks to our hardware analyzer, like the Great Fat Rhododendron or anything else. The decoders are what take that data from the backend and then try to parse it as much as they can into a more friendly format. Anytime an individual decoder takes some data, it will pass it back along to as many decoders as it can and try to parse that data as far as it can possibly go. And then once it's finally done, it will send that to whatever front end you want. If you want a TUI or a GUI, whatever you want. And all of this is very easy to implement yourself, which
To
we'll
the
get
point
more
of
into.
that, part of why I am here right now at this conference talking to all of you is because I really love producing open source things. When an open source project goes well, it is other people picking this stuff up and doing things they love with it, both because it's very inexpensive, they just go and clone the software for free, and because when they go and build their own USB analyzer hardware, or hardware that can incidentally do USB analysis, they can take the software, modify it a little, and be able to kind of run their own USB analysis stack on top of their hardware.
And speaking of implementing backends, Kate managed to.
So I'm here partially to convince you that it is super easy to implement your own backends. In order to do that, one of the things that I did starting around Wednesday was implementing a backend for OpenVizsla. So OpenVizsla, up until this point, which is a project that I have no real affiliation with, had no software front end. It's a pity because a bunch of them were given out via Kickstarter. They are nice hardware. You can go and buy them still. People like TNT have done a lot of work in getting them up and running again. But the software stack for OpenVizsla is still super lacking as of Wednesday. So I started looking at the software stack. It was basically one Python file. One Python file for the communications, and then there's a Python front end for it that accepts the command line arguments. That one file did a ton of low-level stuff. Did a lot of like, hey, send this register right to the target board. And it was just, I won't say it was horrific to look at, as I think that's really an aesthetic thing, but it definitely was kind of like sitting there and going, I was kind of going like, okay, I really don't want to put this in the rest of my code base because I'm just like super neurotic about this. So Wednesday I sat and rewrote the OpenVizsla software stack. So there's now PyOpenVizsla. PyOpenVizsla is a proper Python module. The C backend for this, some of the functionality is still the same, but the Python code has been completely refactored. So if you want, you can now just, I'll probably upload this to pip once I'm sure it's stable, so you'll be able to type in pip install PyOpenVizsla and get an OpenVizsla software stack. This doesn't do any of the analysis, but it is a neat, easily organized stack that lets you use USB captures in your own applications, which was super easy for, which made it super nice to actually capture data from, from a device like that. And I will show you how simple that is in a second. Let me just switch to my terminal. Close out of this. It's really hard to see where my mouse is on this thing. There it is. I'm just gonna open another new terminal. You want to talk through what I'm doing?
Yeah, so the OpenVizsla backend is something that what are you doing right now? Something that Kate in particular implemented, very, very quickly, and that's because implementing a backend for ViewSB, the software, is only really as difficult as interfacing with whatever your backend is, which is why Kate rewrote OpenVizsla's software stack to make exactly that easier.
Just to kind of show you what that looks like actually as I do this. This is the entirety of the backend code for, this is the core that does the USB processing code for the OpenVizsla device. There's code not on here that opens the OpenVizsla device and hooks up the right callback, but this callback is called every time OpenVizsla wants to report a USB packet. The whole code here for analysis, can I put a laser pointer, is essentially if we have a raw packet, we wrap it in a ViewSB packet. We say create from a raw packet an actual analyzer packet, and we submit it to our to the analysis stack for analysis. So raw USB packets are all handled by the analysis stack from there. So if you have a USB analyzer that you're implementing, you need to open a connection to it, start your packet flow, and then we do the rest. This is running in its own process, which means that you can sit there and do your packet checking in a while loop, and it will not affect the analyzer. It is designed to be as simple for people to implement these modules as possible. And what that means is that you can sit there and spin wait, capture packets, and just submit them. they'll automatically go over a pipe to the main analyzer process, which will handle those asynchronously for you. You do not have to do anything beyond write the Python code that captures stuff from your device. Question?
I noticed you're skipping zero-length data packets.
This is actually not, this is encoded packet, so it's not the data packet itself. The data packet still has the header on it. So this is actually just if we're getting, sometimes OpenVizsla spuriously calls the callback. So this is actually just, we're not skipping ZLPs. So yeah, if you're a USB person, then you know that zero-length packets are actually an important part of the protocol. So this is on the raw packet level, not on the data packet level. So you'll get a data transaction that says, okay, right after your token, you get the data packet. It still has a header and a CRC on it. So that actually winds up coming in here anyway. So let me show you what the capturing from OpenVizsla looks like, assuming I managed to close the device previously. And let me open just the CLI version. The CLI version is a super primitive debug tool. I need to run demo, not with a USB program. Demo
It's
CLI.
simple to the point where we're basically just printing the data that we get, like almost
I
as
don't think this is
raw as we can.
demo CLI OpenVizsla.
Yeah, there you go.
And I have to actually have USB OpenVizsla plugged in. I am very, very, very good at USB, you can tell.
Very good at USB lab demos.
I actually have only 2 USB-A ports on my laptop, so I'm swapping between the presentation remote and OpenVizsla. So here we go. I have an OpenVizsla device plugged in. I do not have any data going through it. If I plug in a device into OpenVizsla and have it enumerate itself, I see data from OpenVizsla. This is just, I have the analysis stack actually off. Thank you. So this is without the analysis stack running. This front end just prints things. This is literally seeing the data I'm getting from the OpenVizsla raw. So with one modification, I do group them into transactions because otherwise this makes a really poor demo.
And
This is
because
all
you don't
really
know when to
difficult
stop.
see. Yeah, and well, I don't know where to stop even when I'm implementing demos, I guess.
Yes, which is why you use those characters to make that nice tree view.
Yeah, that is true. I use Unicode. So this is just a really raw view of packets coming from OpenVizsla. And this is just implementation of a single backend. It's not particularly good until you start adding in decoders. And decoders on this are super simple. Super, super simple. This is a standard request decoder that happens to, like, if you have a standard request something that USB is already doing, you implement basically a boilerplate type. This is the entire parsing for the standard request that is set address. This is all you have to write. Essentially, all this thing does, you fill out some fields, you fill out a summary, super easy. If you want to create something that's more complicated, an analyzer that does things that's not at this level, it's not just if you want to implement your own vendor request analyzer or anything like that, then you really have the responsibility of writing 2 functions, essentially. One of them is your summary function. So there's a set of summary functions you can implement. By default, summarize is enough to give you a text description of the packet. You could say summarize data, which gives you a bigger description of the data payload. There's a bunch of other little things that you can implement. And there is a function called consume packets. Consume packets, you choose whether or not you want to consume a packet that's going through the analyzer stack. If you do, you can then re-emit another formatted packet to the stack. So if you implement the consume packets function, you get a nicely formatted USB level packet that you can then manipulate and decode and change into something nicer. There does not have to be a one-to-one relationship between the packets captured, packets consumed, and the packets decoded. So you are free to, for example, grab 3 packets and emit 1, which is useful for like the transaction grouping that we just saw.
In fact, very frequently that is the case because USB has a habit of liking to group things into 2 or optionally 3.
So what you're actually seeing is USB is accepting those USB packet structures that you saw being created in the OpenVizsla backend here. It is taking them, interpreting them. So it says, okay, I've got a token packet, a data packet, and a handshake packet, the kind of fundamental piece of USB transactions. And it squishes those all into a single USB transaction object, which then kind of consumes 3 and emits 1. And typically when you consume them, you can leave them as subordinate packets. They all wind up displayed in your front end. And I'm trying to go to the next slide by typing into my terminal. And I call myself a software person, sort of. I'll give you the presenter back.
You don't really, but
Yeah, I don't.
and speaking of front ends, again, the design of USB is modular enough that you can implement a front end simply by writing a function like, oh, that's right, you unplugged the presentation remote.
You can hit next. Yeah, sorry.
Yeah.
I handed it back to you and I was setting you up for failure.
Yep. All you really need to say is define a function, it's handle incoming packet, and then do whatever you want to do in your own front-end logic, which makes, again, as with the backends, implementing a front-end is really only as difficult as fighting whatever front-end software you're going to use, like Qt, which is what I've been doing.
So all that you have to do is handle this function when it is, essentially you get a queue of data. There's a built-in function that you will call handle incoming packet on that queue if you want to use that boilerplate, if you can handle updating your data on an event loop. But this also runs in its own process, which means that you get everything here kind of for mostly free, and it's being its own process based. You can while loop, you can do whatever you want to. You're not going to stall the analyzer. So let me show you an example front end for this. This is one of a few examples that we've created. Mikaela has been creating a Qt UI, which is a kind of cross-platform UI that has proper GUI properties, but like 2 days ago, she said that she would love having a text UI interface, the curses interface to this thing.
An offhand remark.
Because then it would be nice to just like SSH in and be able to touch USB stuff. And I made the mistake of looking into, I wonder if there are nice things that wrap curses these days. And sure enough, there are. And by the time I looked at that, I had it was like the next morning, and I had implemented a text UI. And so let me actually use some pre-captured packets so I don't have to mess with them. And so let's see what I've got here. Pre-captured USB.bin. Definitely the best way to navigate through here. So this is the text user interface. And the text user interface is this has the full analysis stack behind it now. It is taking all of the packets that you get, interpreting them through the full decoder stack. I haven't written decoders for everything here, but what you're actually seeing is there's a USB hub inline during this capture that is reporting the status of the device as you plug it in. You see the device descriptor. The device descriptor is parsed. You have a packet view on the right. So essentially from the view of raw hex, you get kind of a view out of this that arises that is that's pretty well decoded. Implementing descriptor types is super easy. You implement like one little data structure and you get all this stuff out of it. So this thing is super easy to use for analyzers, especially if you're just saying, okay, I want to add a hit descriptor analyzer to this. I want to add something that can interpret mouse packets.
Implementing descriptors is simple enough to the point where often all you really need to do is specify the USB standard names of the descriptor because they have things like the size encoded in them.
Yeah, so I did a lot of syntax sugar for this stuff. This is the text user interface. There's also a Qt user interface that is in progress, but trying to get Qt working on a computer that's different than Mikaela's during a demo is kind of frightening to me. So this is kind of the demoable version of this right now. This is all on GitHub, by the way. So if you have any of these devices, you can go and use this right now. But not everyone has these devices, so looping back to the beginning, I implemented proper USB mon support. Actually, that was on the plane 2 teardown. I didn't want to be sitting there on a tray table plugging and unplugging USB devices, having nests of wires, both because airline flight attendants don't tend to take well to you having like 15 different embedded systems on your tray table. And it's just generally a nice thing to have that I'd love to use in the training. So if I tell this instead of using pre-captured data, let's quit out of this and tell it to use, I think it already used USBmon. Hold for a second.
Might as well just plug in the yeah. So USBmon again is the kernel module. So all you have to do theoretically is load the module, and hopefully in a live demo everything will work fine. And if you use that on Mon 0, that gets everything that's going through all of your USB buses, USBs, and
Plug-in device. You want to announce that?
Yeah, and so Kate's going to plug in a great-fet, and hopefully we're going to see enumeration. Right now we're just getting the things like the hub
So this
data. Yep.
This live analysis here is happening as I'm plugging in this great-fet. You can actually see it's saying, I got a device. It is a great-fet. You can see the string is going through here. It's a great Scott Gadgets great-fet that I'm plugging in. This is happening just using a software analyzer on Linux. So
The same software analyzer that Wireshark was using.
And you do not have to know what an herb is. You do not have to know what negative E pipe means. I looked in the kernel source, figured that out for you, and I decoded into stuff that is USB. So, what that means is if you have a Linux device, even a Raspberry Pi, you can do things like USB analysis with it, up to theoretically super speed, because Linux will talk super speed. Good luck understanding the thousands of bulk transactions that happen if you actually have something that's using the full nature of super speed, but this can theoretically parse that. So that is kind of the whole demo here. So this is USB. It is on GitHub. I went about a year ago to register an organization for the set of USB tools we had, typed in the organization name USB tools, and somehow in 2018, whenever it was, the USB tools organization name was still available. So it is github.com/USB-tools.
I think that shows how little people think about USB, how much people think about USB
Yeah,
as
I'm
black
really
magic.
surprised no one was name squatting that. So from here I had bonus slides. I'm not going to go through the bonus slides because I kind of knew that we'd be out of time here, but I will open the floor for questions. And before I do that, one last thing here is, I think I have 1 minute for exactly
We have
one
exactly
question.
a minute, basically.
But what I'm kind of imploring everyone to do, especially as we have basic Linux USB Mon support, grab this. If you want to write a decoder, if you implement a device, go ahead and contribute a decoder for it. This is the kind of thing that is much better if we all work on it together.
Or
And
Frontend.
I think this is really kind of filling a niche that I've wished something existed in for years. I'm super excited about having this support. One question. Anyone?
I'll just say it loudly.
Yeah,
So
I'll repeat your question.
Is the round trip to a URB and back lossless, or are you losing a little bit?
So the question is, when we process the herbs that Linux submits back and forth, is that lossless? And the answer is that is not lossless. So I'm generating USB transfers from those. You will see in the analyzer only the transfer level. You will not see the individual packets. So you're limited by what your analyzer can do.
We can kind of gather what some of the packets were, but we're not going to get much more than that.
All right, awesome. Thank you all so much. I will be outside if you have further questions. All right, I'll be out there if you have further questions. I'm going to gather my stuff and get off the stage so that you can continue this. But thank you so much for coming.
Thank you.